Fine. Let's start. Number 15. The satellites overhead. Right now, about 20,000 kilometers above your head, there are little machines flying in slow circles around the planet, and every single one of them is haunted by a problem Einstein warned us about over 100 years ago. They're GPS satellites. You've used them today. Maybe to find a coffee shop. Maybe to avoid a wrong turn. Maybe just because your phone quietly knows where you are at all times. And the whole thing only works because engineers were forced to admit something deeply strange. Time up there does not run at the same speed as time down here. Here's what's going on. A clock on a GPS satellite is far from the Earth, where gravity is weaker. And in weaker gravity, time runs a little faster. So the satellite clock gains about 45 millionths of a second every day, just from being high up. But that same satellite is also moving fast, screaming around the planet at thousands of kilometers an hour. And when you move fast, time runs a little slower. So it loses about 7 millionths of a second a day from the speed. Put those two together, and the clock in orbit ends up running about 38 millionths of a second fast, every single day, compared to the clock on your wrist. Now, 38 millionths of a second sounds like nothing. It sounds like a rounding error. But here's the thing. GPS works by timing radio signals down to the nanosecond, and light travels about 30 centimeters in a nanosecond. So if you ignore that tiny relativistic drift, the errors don't just sit there. They pile up. Your position would be wrong by about 10 kilometers after a single day. Your navigation app would confidently place you in the next town over, and it would get worse every hour. So the engineers did something that should give you pause. Before these satellites ever launched, they went into the factory and deliberately set the clocks to tick at the wrong rate. They slowed them down on purpose, so that once they were up in orbit, moving fast, sitting in weaker gravity, they would drift into being exactly right. They built the correction for a 100-year-old theory of time directly into the hardware. We like to think of time as this steady, universal thing. 1 second here is 1 second everywhere. But your phone doesn't believe that. Your phone can't afford to believe that. Every time it finds you on a map, it's quietly accepting that the sky and the ground disagree about what time it is, and always will. The most ordinary device you own is a monument to how strange time actually is, and we mostly just use it to avoid traffic. Number 14. Your head and your feet. Let's bring this down from orbit and into your living room, because it turns out you don't need a satellite to pull time apart. You just need a really, really good clock and a staircase. In 2010, physicists at the National Institute of Standards and Technology in the United States took two of the best atomic clocks ever built and set them up next to each other. Then they raised one of them by 33 centimeters, about a foot, the height of a single step, and they watched what happened. The higher clock, the one just slightly further from the center of the Earth, started ticking faster than the one below it. Measurably. Repeatably. Exactly the amount Einstein's math said it should. Think about what that means for a second. Gravity is stronger closer to the ground, and weaker further up, and time runs slower where gravity is stronger. So the clock nearer your feet runs slow, and the clock nearer your head runs fast. Which means, if you're standing up right now, your head is aging faster than your feet. I want to sit in that for a moment, because it sounds like a joke, and it isn't. It's real. If you spend a lifetime standing upright, the top of your body will end up very slightly older than the bottom. We're talking about 90 billionths of a second over an 80-year life. It's not going to give you wrinkles on your scalp first. Nobody's forehead is going gray ahead of schedule. But here's the thing. The size of the effect is not the point. The existence of the effect is the point. Time is not one thing happening to all of you at once. Your body is spread across a tiny range of heights, and every one of those heights is moving through time at a slightly different rate. You are not a single object experiencing a single now. You are a stack of slightly different clocks, glued together by biology, and they didn't stop there. In 2022, a team in Colorado managed to measure this same effect across a single millimeter, the width of a pencil tip. They took a cloud of 100,000 ultra-cold atoms and detected that the top of the cloud aged differently than the bottom of the cloud. We used to think you needed black holes and light speed to see relativity. Now, we can see it across the length of a sugar cube. You are not one age. You never were. You're just too big to notice. Number 13. The clocks that flew around the world. You've heard of the twin paradox. It's the classic. One twin gets on a spaceship, flies off near the speed of light, comes back, and finds the twin who stayed home has aged decades while they've barely aged at all. It's the kind of thing that shows up in science fiction, and it's easy to file it away as a fun thought experiment. Something that's technically true, but would never actually touch your life. Except it already happened. On real clocks, on a normal commercial airliner, in 1971. Two scientists, Joseph Haffel and Richard Keating, had a wonderfully cheap idea. Instead of a spaceship, they'd use the fastest thing they had easy access to, which was a passenger jet. They took 4 atomic clocks, bought them their own seats, and flew them all the way around the world. First heading east in the direction the Earth spins. Then they did it again heading west, against the spin. The whole experiment cost about $8,000, which makes it one of the cheapest tests of Einstein's theories ever run. Then they brought the clocks home and compared them to identical clocks that had stayed put at the U.S. Naval Observatory. They didn't match. The clocks that had flown east had lost about 59 billionths of a second. The clocks that had flown west had gained about 273 billionths of a second. And these weren't errors. These weren't glitches. The differences lined up, within the margins, with exactly what relativity predicted when you combine the effect of speed and the effect of altitude. Here's the thing that gets me. The direction mattered. Flying with the Earth's rotation and flying against it produced different results, because your speed through space is different in each case, and time responds to that. The universe was keeping a slightly different account for each clock, and it settled the bill down to the nanosecond. So the twin paradox isn't a metaphor. It's not a maybe. Every time you take a flight, you come home a tiny, tiny fraction of a second younger than you would have been if you'd stayed on the ground. A frequent flyer has genuinely lived less time than the person who never leaves home. Not in a poetic sense. In a we measured it sense. You can travel into your own future. You already have. You just did it so slowly, you'll never feel it. Number 12. The particles that shouldn't reach you. Right now, as you're listening to this, particles are passing through your body. Not metaphorically. Physically. Silently. Constantly. Tiny fragments of the universe are falling through you, like you're not even there. And the fact that they reach you at all is one of the cleanest proofs we have that time can bend. They're called muons. They're born high up in the atmosphere, about 15 kilometers above the ground, when cosmic rays from deep space slam into the top of the air and shatter. A muon is like a heavier, unstable cousin of the electron. And the important thing about a muon is that it does not live long. On average, a muon exists for about 2 millionths of a second before it falls apart into smaller particles. That's its whole life. Blink and it's over, 1,000,000 times over. Now here's the problem. Even moving at almost the speed of light, a muon should only be able to travel about 600 meters before it decays. 600 meters. But it's born 15 kilometers up. Do the math, and it's not even close. By every rule that should apply, these particles should die high in the sky, thousands of meters above your head. You should never, ever feel them. And yet detectors at sea level are drenched in them. They pour through the roof, through the ceiling, through you, roughly one passing through your hand every second or so. So how do they get here? Here's the thing. From our point of view, standing still on the ground, the moon's internal clock is running slow. It's moving so fast that time itself stretches out for it. That 2/millionths of a second lifespan, as we measure it, gets extended by a factor of about 9. Suddenly, it lives long enough to cross the whole atmosphere and reach the ground. Physicists actually confirmed this back in 1941, comparing how many muons they found on mountaintops versus down at sea level. The numbers only make sense if time is bending. So think about what that means. There is a rain of particles falling through your body every single second that only exists because their time runs slower than yours. If time were rigid, if a second were a second everywhere, they'd all be gone before they got anywhere near you. Their extra life is borrowed. Stolen, really, from the difference between their clock and ours. You are being gently, constantly passed through by the evidence. Time dilation isn't happening in a lab across the world. It's happening in the air in front of your face. And it's happening in you. And you never felt a thing. Number 11. The day that keeps getting longer. 24 hours in a day. It's the most solid, boring, dependable number in your life. The sun comes up, the sun goes down, and it takes a day. And a day is 24 hours. It feels like a law of nature, like something carved into the universe. It isn't. It's a snapshot of a number that's been changing for billions of years, and it's still changing right now. Here's what's happening. The Earth's spin is slowing down. Every day is a tiny bit longer than the day before it. The reason is the moon. The moon raises tides in our oceans, and those tides drag against the spinning Earth like a giant brake. That friction very gradually slows us down. And by the laws of physics, the energy has to go somewhere. So it goes into the moon, which very slowly drifts away from us. We can actually measure this. The moon is retreating from the Earth at about 3.8 centimeters a year, roughly the speed your fingernails grow. Now, the day is only getting longer by about 1.7 thousandths of a second per century, so you are never going to notice this. But run the tape backwards across the deep history of the planet, and the numbers get genuinely strange. Go back to the age of the dinosaurs, and a day was noticeably shorter. Go back further, hundreds of millions of years, and you find it in the fossils. Certain corals lay down a fine growth band every single day, like tree rings, but daily. And if you count the bands in a year from 400 million years ago, you don't get 365. You get more, because back then, a day was only about 22 hours long. The year was the same length, but the days were shorter, so there were more of them. And here's the part that really got scientists' attention. Go back even further, more than 1 billion years, and there's evidence the day got stuck. For roughly 1 billion years, the day held steady at about 19 hours and refused to budge. The best explanation is that the sun heats the atmosphere and creates its own kind of tide, a tide in the air, that pushes the Earth to spin faster. And for 1 billion years, that push almost perfectly canceled out the moon's drag. Time, in a sense, dug in its heels. So here's the thing. There is no true length of a day. There never was. The 24 hours you live by is a number caught in mid-slide. The dinosaurs lived shorter days than you do. Your distant descendants will live longer ones. And the whole time, the moon keeps pulling away, quietly stretching your days out beneath your feet. The most reliable number in your life is a moving target. You just don't live long enough to watch it move. Number 10. The speeding clock inside you. Ask anyone over the age of 40, and they'll tell you the same thing. Time is speeding up. Summers used to last forever. A school year felt like a geological age. And now, somehow, it's December again, and you're not sure where the year went. And the years seem to be arriving faster and faster, like train stations at the end of a journey. This isn't just nostalgia or complaining. It's real. And neuroscience has some genuinely unsettling ideas about why. Your brain doesn't have a clock in it. Not a real one. Not like the one on your wall. Instead, it seems to measure the passage of time by how much change it notices. How many new things happened. How many distinct moments got laid down as memory. When you're a child, everything is new. Every day is packed with first times. New faces, new places, new rules about how the world works. Your brain is recording constantly, richly, in high definition, and when you look back, all that dense memory feels like a huge stretch of time. But as you get older, life gets more familiar. The route to work is the same route. The routine is the same routine. And your brain, being efficient, stops bothering to record it in detail. Why store something in high definition when you've seen it 1,000 times before? So the days blur together. Fewer new memories get laid down. And when you look back on a year that was mostly routine, there's barely anything there to measure, so it feels like it flew by. Recent research even suggests that the brain physically changes state less often as we age. The patterns of activity that mark one moment from the next come slower and stick around longer. Fewer mental tics. And here's the thing that really lands. If your brain measures time by change, and change slows down inside your head, then time genuinely feels faster from the inside. Not as a mood, as a mechanism. So this is the quietly frightening part. The second half of your life will very likely feel shorter than the first, even if it's exactly the same number of years. And the more your days repeat, the faster they'll seem to slip away. There's a strange kind of hope buried in that, though, because it also tells you how to fight back. Novelty. New places, new skills, new people, anything that forces your brain to start recording in high definition again. You can't add years to your life this way, but you might be able to make the years you have feel longer. The clock isn't on the wall. It's behind your eyes, and left to run on autopilot, it speeds up every year you let the days repeat. Number 9. What light feels. Look at a star tonight. Any star. The light hitting your eye left that star years ago. Sometimes thousands or millions of years ago, crossed an unimaginable emptiness, and ended its journey on your retina. We say the light is old. We say we're seeing the past. And that's true from where we're standing. But here's a question almost nobody asks. What was that journey like for the light? And the answer, according to relativity, is one of the strangest facts I know. For the light itself, the journey took no time at all. None. Zero. Let me try to explain how that's even possible. In relativity, the faster you move, the slower your clock runs, as seen by everyone else. Push right up to the speed of light, and time slows down all the way to a stop. Light travels at the speed of light. That's its whole nature. So for light, that clock doesn't just run slow. It stands completely still. The mathematics is clean and brutal about it. The amount of time that passes along a beam of light from its own point of view is exactly zero, no matter how far it travels. So think about what that actually means. A photon of light leaves a galaxy on the far side of the universe. It travels for 13 billion years, by our clocks, across an ocean of space, so vast we can barely write the number down. And then it lands in a telescope on Earth. From our side, that's 13 billion years of travel. From the light's side, the moment it was created and the moment it was absorbed are the same moment. It was emitted, and it arrived in the same instant. No journey, no waiting, no time. But here's the thing that really turns my stomach in the best way. If light experiences no time, then in some sense, for the light, the distance doesn't exist either. The far edge of the universe and your eyeball are touching. The birth of that photon and its death on your retina are pressed right up against each other, with nothing in between. Every time you see anything at all, you are catching something for which the entire history of its trip across the cosmos happened in no time at all. The starlight doesn't feel old. The starlight doesn't feel anything. From its point of view, it was born, and instantly, it was you. We move through time whether we like it or not. Light gets to skip the whole thing. Number 8. The smallest piece of time. We treat time like water, like something smooth and continuous that flows without any gaps, that you could slice into smaller and smaller pieces forever. Half a second, 100th of a second, 1/1,000,000th. And surely you could always go smaller, right? There's no such thing as the smallest possible amount of time. Except there might be, and it has a name and a number, and beyond it, our entire understanding of physics simply falls apart. It's called the Planck time, and it comes from taking 3 of the most fundamental constants in all of physics: the speed of light, the strength of gravity, and the constant that governs the quantum world, and combining them in the only way that gives you a unit of time. What comes out is a number that is almost impossibly small, about 5 times 10 to the minus 44 seconds. To write it out, you'd put a decimal point, then 43 zeros, and then a 5. It is to 1 second roughly what 1 second is to a span of time vastly longer than the entire age of the universe. And here's the thing. It's not just that this interval is tiny. It's that when you ask physics what happens on a scale smaller than the Planck time, physics stops answering. Our 2 great theories, general relativity, which governs gravity and the very big, and quantum mechanics, which governs the very small, flatly contradict each other down there. The equations don't just get hard. They break. They give nonsense. To go smaller than the Planck time, we would need a theory of quantum gravity, and after a century of trying, we don't have one. So this raises a genuinely dizzying possibility. What if time isn't smooth at all? What if, at the very bottom, it comes in tiny indivisible chunks, and the smooth flow you feel is just an illusion? The way a movie feels continuous, even though it's really just 24 still frames a second. What if the universe has a frame rate? Nobody knows for sure. This is right at the edge of what we can even talk about. But sit with it. The moment you're living in might not be a smooth, unbroken now. It might be a rapid series of separate, disconnected ticks, each one utterly cut off from the last, with a hard floor beneath them where the word when stops having any meaning at all. You feel like you're flowing through time. You might be flickering through it, and the gaps between the flickers might be where reality itself runs out of things to say. Number 7. The present that isn't shared. Here is something you believe without ever thinking about it. You believe there is a now, a single present moment that stretches across the whole universe. Whatever is happening on Mars, or in the Andromeda Galaxy, or on the far side of the cosmos, it's happening right now, at the same time as you sitting there. There's one shared present, and everyone and everything is riding it together. Relativity says that's false. There is no universal now. And the way it shows you is so simple, it's almost cruel. The physicist Roger Penrose made it famous with a scenario. Picture 2 people passing each other on a sidewalk. One is walking toward the Andromeda Galaxy. The other is walking away from it. They pass shoulder to shoulder at walking speed. Nothing dramatic. Nothing fast. And here's the thing. Because of the way relativity treats motion, those two people do not share the same now at Andromeda. Their present moments out at that galaxy are different by days. Let me say that again, because it sounds impossible. Two people walking past each other on a normal street, at a normal pace, disagree about what is happening right now in a distant galaxy, and not by a fraction of a second, by days. For one of them, the Great Fleet is still sitting in its harbor. For the other, walking the other way, that same fleet has already launched. Same instant, same sidewalk, two different presents, separated by days, just because they're strolling in opposite directions. This isn't a trick of when the light reaches them. It's deeper than that. It's about how relativity slices up space and time. Every observer carries their own slice of now through the universe, and the faster and the further you go, the more those slices tilt away from each other. At walking speed and across a room, the difference is nothing. At walking speed and across 2.5 million light years, the difference is days. And here's where it gets genuinely disturbing. Some physicists take this and run all the way with it. They argue that if the future for one person is already the past for another, then the future must already exist. Every moment, past, present, and future, all sitting there equally real, all at once, in a giant frozen block. On this view, tomorrow isn't coming. Tomorrow is already there. And so is the day you were born, and the day you die, all of it existing together. And your feeling of moving through it is just that. A feeling. There is no shared present. There may be no flowing present at all. There's just you, carrying your own thin slice of now, convinced everyone's riding the same wave you are. They're not. Nobody is. Number 6. The edge where time stops. Imagine you're watching a friend fall into a black hole. It's a grim thing to imagine, so let's at least make it interesting. You're a safe distance away, floating, watching them drift toward the event horizon, the point of no return, the edge beyond which not even light can escape. What do you see? You'd expect them to fall in, to accelerate, to plunge over the edge, to vanish. That's not what happens. Not from where you're floating. Instead, as your friend gets closer and closer to the horizon, you see them slow down. The closer they get, the slower they move. Their motion drags out, stretches, grinds toward a halt. Their light shifts redder and redder, dimmer and dimmer, as if they're fading into the dark, and they never quite reach the edge. They just hang there, frozen, forever, an image of a person pressed against a boundary they never seem to cross. Astronomers used to call black holes frozen stars for exactly this reason. From the outside, things don't fall in. They freeze on the doorstep and slowly fade to black. Here's the thing, though. From your friend's point of view, none of that is happening. They don't feel themselves slow down. They don't freeze. They fall right across the horizon in a perfectly ordinary amount of time, seconds maybe, without anything special marking the moment they cross. They sail straight over the edge and into whatever waits inside, while to you, they're still stuck on the threshold, hanging there for all eternity. So now we have a problem that should genuinely bother you. Did your friend fall into the black hole, or didn't they? Because you have two completely honest observers, and they will never agree. To you, it never finished happening. To them, it was over in seconds, and there is no higher court, no master clock, no view from nowhere that can settle it and tell you who's right, because they're both right. The event has no single truth. It has two, and they contradict each other, and the universe is completely fine with that. This is the part of relativity that I think is genuinely the hardest to swallow. We want events to be facts. A thing happens or it doesn't. But near a black hole, whether something has even happened depends entirely on who is watching and how they're moving. Time doesn't just slow down out there. It comes apart. It splinters into separate stories that can never be stitched back together. Somewhere out there, right now, there are black holes with the frozen, fading images of everything that ever fell toward them, still hanging at the edge. Ghosts on a threshold. Events that, from the outside, have been not quite happening for billions of years. And they'll go on not quite happening long after you and I are gone. Number 5. The loops in the equations. Time travel into the past. It's the oldest wish in science fiction. Undo the mistake. Warn the past. Meet your grandparents. Kill the villain in the crib. And we all know deep down that it's impossible. The past is gone. You can't go back. It's a fantasy. Except our best theory of gravity. Einstein's general relativity. The same theory that runs your GPS and predicts black holes with terrifying accuracy does not agree that it's impossible. In fact, tucked inside its equations, there are solutions that describe exactly that. Paths through space and time that loop back around and return to their own past. Physicists call them closed time-like curves. And they are not a mistake in the math. They're really there. The first one showed up in 1949. A brilliant logician named Kurt Gödel, a close friend of Einstein's, was playing with the equations and found a solution describing an entire rotating universe. And in that universe, if you traveled the right path, you could come back to your own starting point in time. You could visit your own past. Einstein himself was reportedly disturbed by it. His theory permitted something that should have been forbidden. And Gödel's wasn't the last. Take a rotating black hole, described by the Kerr solution, and inside it, the equations again allow paths that loop through time. Imagine an impossibly long, impossibly dense cylinder, spinning at a fantastic rate, the so-called Tipler cylinder, and once again, loops into the past appear. Spinning cosmic strings can do it too. Over and over, when you let things rotate hard enough in general relativity, the door to the past creaks open. Now here's the honest part, because I don't want to oversell this. Every single one of these solutions requires something absurd. An entire universe that rotates when ours doesn't. A cylinder that's infinitely long. Matter squeezed to impossible densities. Exotic ingredients we've never found and may never find. So nobody thinks you're going to build a time machine this way. And Stephen Hawking even proposed what he called a chronology protection conjecture, the idea that the universe has some deep, not yet understood mechanism that steps in to forbid these loops and keep history safe. But here's the thing. A conjecture is a guess. It's a hope. It has never been proven. And in the meantime, the plain fact remains. The laws of physics, written down in their full glory, do not actually rule out returning to the past. The prohibition we all take for granted, the one thing we're absolutely sure about, that what's done, is not in the equations. We put it there ourselves, because the alternative is too strange to live with. The math left the door unlocked. We just really, really hope nobody figures out how to walk through it. Number 4. The arrow made of disorder. Here's a question that sounds childish and turns out to be one of the deepest in all of physics. Why does time only go forward? You remember the past, not the future. A cup falls off the table and shatters, but shattered cups never leap back up and reassemble. An egg scrambles, but never unscrambles. Time has a direction, an arrow pointing firmly from past to future. Why? You'd think the answer would be simple. It is not. Because here's the thing that stops physicists in their tracks. When you look at the fundamental laws of nature, the deep equations that govern how particles move and forces work. Almost none of them care about the direction of time. Run them forward, run them backward. They work exactly the same either way. At the level of individual particles, a movie of physics played in reverse looks perfectly legal. Nothing in the basic rules says the cup can't unshatter. So where does the arrow come from? Where does the one-way street of time actually live? The answer, as far as we can tell, is a single law. The second law of thermodynamics. The one that says entropy, which is basically the amount of disorder in a system, always increases. Order falls apart. Heat spreads out. Things mix, and they never spontaneously unmix. The cup shatters because there are countless ways for it to be broken, and only a few ways for it to be whole. So overwhelmingly, disorder wins. That relentless, statistical march from order to disorder is the arrow of time. It might be the only reason time has a direction at all. And here's the part that should genuinely unsettle you. If the arrow of time comes from entropy increasing, then it depends entirely on the universe having started in a state of incredibly low entropy. Extraordinarily ordered, almost impossibly neat. For some reason we still do not understand, the universe began in a state of exquisite order, and everything since, all of cosmic history, all of your life, is just that order slowly, inevitably unraveling. The future is simply the direction in which the mess increases. So the flow of time isn't a fundamental law handed down from on high. It's a byproduct, a side effect of a statistical tendency, riding on top of a starting condition nobody has fully explained. Your entire sense that yesterday is fixed and tomorrow is open, that you're moving forward and not back, rests on the fact that the early universe was, for reasons unknown, unbelievably tidy. The deepest laws don't know which way time goes. Only the mess does. And every moment that passes, the mess gets a little bigger, and that, and maybe only that, is what we call the future. Number 3. The flicker we live in. We think of the universe as old, 13.8 billion years. That's an enormous number, way beyond anything a human mind can really hold. It feels like the universe has been around forever, and that we're living somewhere deep in its long, mature life. We're not. We're living at the very, very beginning, right at the dawn. And when you see how the whole story of the universe actually stretches out, the age of stars we live in, the bright cosmos full of light that we think of as just how things are, turns out to be a tiny flicker at the start of something almost endlessly long and almost endlessly dark. Cosmologists sometimes divide the future of the universe into eras, and the scale of them is genuinely hard to process. Right now, we're in what's called the Stelliferous Era, the age of stars, galaxies shining, new stars being born, the whole spectacle. It's beautiful. It's also temporary, because stars need fuel, and eventually the gas to make new ones runs out. The last stars will flicker on somewhere around 100 trillion years from now, and then no new stars will ever be born again. But 100 trillion years is nothing compared to what comes next. After the stars die, the universe enters the degenerate era, lit only by the cooling embers of dead stars, white dwarfs, and neutron stars, slowly fading. That era lasts vastly longer than the age of starlight ever did. And then even those remnants decay, and you're left with the black hole era, a universe that is nothing but black holes, slowly, unimaginably slowly, evaporating into the dark. And that lasts longer still. We're talking about a length of time you write as 10, with 100 zeros after it. And then, after even the black holes have boiled away, comes the dark era. Cold, empty, silent, and effectively forever. So here's the thing I want you to really feel. Everything you have ever known, Every star you've ever seen, every sunrise, all of human history, all of life on Earth, the dinosaurs, the pyramids, the entire age of shining stars. All of it fits inside that first bright sliver at the very beginning. If you drew the full history of the universe as a single long line, the part with stars in it, the only part we'd recognize as home would be a bright scratch at the very edge, and the rest of the line, stretching off into distances the numbers can barely describe, would be dark. We don't live in an old universe. We live in a newborn one. We are the earliest of early risers, standing in the brief morning of a night that goes on almost forever. Make the most of the light. It's rarer than we ever imagined. Number 2, the end of time itself. We just walked out to the far end of the universe's life. The dead stars, the lingering black holes, the long slide into the dark. But there's one more step past all of that, and it's the strangest of all. Because it isn't just the end of stars, or the end of matter, or the end of light. It might be the end of time itself. Not time running out. Time ceasing to mean anything. To get there, we have to talk about that word from before. Entropy. Disorder. The universe is always moving from order toward disorder, from concentrated to spread out, from hot spots and cold spots toward one uniform lukewarm sameness. And there's an endpoint to that process. A final state where everything is as mixed and spread out as it can possibly be. No hot, no cold, no gradients, no differences left anywhere. Physicists call it the heat death of the universe. And it's not violent. There's no explosion, no crunch. It's the opposite. It's perfect, absolute, uniform stillness. Now here's the thing, and this is the part that quietly rewires your brain. Think about what time actually is, at the most practical level. Time is how we track change. One thing happens, then another thing happens, and the gap between them is time passing. Every clock ever built works by counting some change. A pendulum swinging. An atom vibrating. Something moving from one state to a different state. That's all a clock is. A change counter. So what happens when there is no more change? In the heat death, everything has already happened. Everything is spread out, evened out, finished. There are no gradients left to drive any process. Nothing can move from one state to another, because there's nowhere left to go. And if nothing can change, then no clock can tick. Not because clocks break, but because there is nothing left for a clock to count. And if nothing can be counted, if no event can ever follow another event, then in what sense does time still exist at all? That's the truly haunting part. Time doesn't stop at the end of the universe the way a film stops when you switch it off. It just quietly stops meaning anything. There's no next moment, because nothing distinguishes one moment from the one before it. An eternity, if you can even call it that, of unbroken, featureless sameness, where the very concept of later no longer applies. The universe doesn't end with a bang. It doesn't even end with a whimper. It ends with a stillness so complete that time itself has nothing left to do, and simply fades out of the story. Everything that will ever happen happens before then, and then, forever, nothing. Number 1. The now you'll never reach. We've gone all the way out to the death of the universe and the freezing edges of black holes. So for the last one, I want to come all the way back in. Closer than anything. Closer than your own skin. Because the most unsettling fact about time isn't out there in the cosmos. It's happening inside your head, right now, as you listen to these words. And it's this. You have never once experienced the present moment. Not for a single instant of your entire life. And you never will. Here's why. Everything you perceive has to travel. Light bounces off the world and takes time to reach your eyes. Then a signal has to fire from your eye to your brain. Then your brain has to process it, sort it, assemble it into an image, and finally push it up into conscious awareness. And all of that takes time. Not a lot. Roughly 80 thousandths of a second for the basics, sometimes longer. But it is never, ever zero. By the time you're aware of anything at all, the thing you're aware of has already happened. It's already gone. You are always seeing a moment that has just slipped into the past. And here's the truly strange part. Your brain hides this from you. It knows about the delay, and it cheats to cover it up. It actually takes its best guess at what's happening right now and paints that prediction over your awareness so that the world feels live, feels immediate, feels like it's happening in real time. It isn't. You're watching a very, very slightly delayed broadcast of reality, edited on the fly to feel instant. The now you feel so certain of is a story your brain tells you a fraction of a second after the fact. And it gets deeper. Stack the light on top of it. When you look at the moon, you're seeing it as it was over a second ago. The sun, 8 minutes ago. A friend across the table. A few billionths of a second in their past. There is no distance at which you ever see anything as it truly is right now. Everything you have ever looked at, everyone you have ever loved, you have only ever seen as they were, an instant or an age ago, never as they are. So put it all together. The outside world reaches you late. Your own brain processes it late. And then it lies to you and calls it now. The present moment, that razor's edge you feel you're balanced on, the one solid thing you think you're standing in, is something you are chasing and can never catch. By the time you reach for it, it's already the past. You are not living in the present. You never have been. You're living a heartbeat behind the universe, watching a beautiful recording of a moment that's already gone, and calling it your life. And maybe that's all right. Maybe a moment already gone is still worth being here for. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.